Hello. In this lecture, we're going to explore some of the set operations that are possible in SQL, and different dialects of SQL implement some of these set operators directly, and others you have to use equivalent logic to emulate them. The set operations we're talking about are union, intersection, difference, and complement. And we're going to explore those using some color sets. So I have a couple of tables out here. The bands table, which I've selected rock bands and popular music bands that have a color in their name and made a note of that color, and the emotions table. And so I've looked up some colors that are associated with different emotions. And so we're going to explore those in the context of intersecting and doing set operations on where the one table's colors intersect or complement, or we can express some other set operation on the colors between these two tables. They really have no particular meaning other than that's a convenient way to do some set operations that are pretty easy to understand. All right, so let's see what we can do to explore these set operations in SQL. And we're going to do this in a way that parallels the assignment exercises. So if you can solve these exercises here, the parallel exercises in the walkthrough, then you should be able to apply what you've learned to the actual exercises in your assignment. Okay, so let's take a look at number one. And the parallel version of this exercise says, using the color set database, list the union of the color fields from the bands table and the emotions table, order the results by the ordinal number of the color field ascending. So the ordinal number, that's just the ordered number of the field. There's only one field, so there's only one to talk about. Why do we bother to use an ordinal number rather than just saying the field's going to be called color? Why not just say color? Well, the reason is, in union of tables, we're not necessarily going to have the same attribute by the same name, even if it is a similar set of values. It simply needs to be union compatible, which means that the data types for the corresponding fields, field 1, field 2, field 3, the ordinals, are either the same type or of compatible types. So varchar and char, for example, would be compatible types. And so we need to have union compatibility. Okay, we're going to refer to it by the ordinal number because that'll work regardless of whether the name of the corresponding fields is the same or not. So it's a useful technique. Otherwise, you could, if they happen to be the same name, you could use the name of the field to align them. Okay, so let's get started on this doing a simple union. Union is going to give us all of the elements in set A and all of the elements in set B. So let's do a union. Use color sets. Actually, we've already used color sets. So let's select color from bands, union, select color from emotions. Okay, and for consistency's sake, I like to break the clauses. It makes it more readable, a little more understandable, I think, to sight read the code. And then let's take the results and order by 1. So referencing that first field that comes back, and we'll do that ascending. And of course, this is kind of redundant because if I didn't say ascending, it would be in ascending anyway. That is the default. And this kind of union is going to, by inference, going to be distinct. It's going to deduplicate the results. So whether black was mentioned once or multiple times, black appears here once, blonde, blue, brown, cream, crimson. And let's take a look at our Venn diagram for the data set and see if we agree that that looks like it is correct. So I should have brown, gray, orange, and yellow. I see brown, gray, orange, and yellow. And I should have the intersected part: black, blue, green, pink, purple, red, white, black, blue, green, pink, purple, red and white, and then I should also have blonde, cream, crimson, rose, and steel. Blonde, cream, crimson, rose, and steel. So good, I've got a proper union of those. Now, if I wanted a unreduced result, if I wanted all of the members of both sets, whether or not they are duplicative, I could say union all, and that is going to remove the distinctiveness of that and give me all the results. And so we'll do this, and here we have multiple blacks, multiple blues. So anywhere it's redundant, I get an entry for each row that had that value. So you can have it either way, just depends on what your case is. And in fact, that was the requirement for our second exercise. So we've already solved that. Let's just put the problem statement up here. It says modify your solution to the previous exercise to use a form of the union operator, which includes all results, even if they are duplicative. All we need is the all operator, and we've got that solution. Okay, so now let's see about getting the intersection. And we're working this term in MySQL, and MySQL does not have an intersect operator, but we can emulate it with equivalent logic. And what we're going to do is use an in clause to select the intersection. And what that's going to look like is select color from bands. That's fine. We're going to start with that. But instead of the union all, let's come over here and modify this so it says where color is in. And then here's going to be our enumerated list. How do we populate that list to get what's the intersection? Well, we say select color from emotions. And so if it's in bands and it's also in emotions, well, that's the intersection by definition, right? And let's do some ordering of that, order by color. And we probably ought to put our problem statement up here just to be consistent. So again, this is going to use the in operator, but the key thing is we're emulating the intersection set operation. Let's run it. And somewhere I have a problem. Let's check it. Select color from bands, where color in, select color from emotions, order by color. I'm not seeing it. Oh, there it is. No error. Okay, and this says the intersection should be black, blue, green, pink, purple, red, red, white, white. And let's see, is that indeed the truth? Black, blue, green, pink, purple, red, white. And again, I did not bother to, when I made my Venn diagram, I did not show the duplicated, I only showed the deduplicated version. And so we could certainly fix that this way if we wanted it to match up. Black, blue, green, pink, purple, red, white. Black, blue, green, pink, purple, red, white. So that is correct. The original problem statement didn't require deduplication, so I'm going to get that out of there. Here is the correct full point kind of solution for the problem as it is currently stated. Great, so that's intersect. Let's move on and see what a difference or a minus operation looks like. And once again, the minus operator is, at this time, the version of MySQL database I'm running does not directly support that, but there's equivalent logic. All we need to do is essentially do a left join, and we can get there. So let's take a look at the problem statement. And problem statement starts with the admonition. Recall that the SQL dialect implemented by MySQL does not directly provide the minus set operator, but this can be emulated using a left join. And there are other logically equivalent ways that will work as well. I've elected to demonstrate this with the left join. And we're going to construct the logical equivalence of set A minus set B. And for set A, we're going to use the band colors, and for set B, we'll use the emotion colors, and we're going to order the results by the band colors ascending. So let's take a look at that. So we want to select bands.color, and you know what, let's do, let's alias band so we don't have to keep typing it. Call it b.color from bands aliased as B. Left join emotions, we'll call that aliased as E. On b.color equals e.color, where e.color, that dot color is null, and we'll order the results by b.color. All right, so let's double check this. This is supposed to be the difference. Let's go grab our Venn diagram again, and it is A minus B, and in this case we need bands A. So I should see everything that's in the yellow over here, nothing that's in the green or the intersection, and none of the purple that's part of the other sets at B. So set A should be blonde, cream, crimson, rose, steel, blonde, cream, crimson, rose, steel. And it's important to double check that because it's really easy to get these reversed and assign set B as set A and set A as set B if you're not thinking about it. And of course, if that's what you want, just a couple ways around that. Use a right join instead of a left join and structure your query that way, or swap bands and emotions everywhere they appear here, and you should get the problem swapped around and you get the other side. All right, let's take a look at problem 5. And 5 is, we're going to get into the complement. So we're going to, let's see the problem statement and we'll talk about it. Okay, so here's the problem statement. Using the set operators used in the previous exercises, list all the band name and emotion colors except those colors that are both band name and emotion colors, or the list in ascending order. In other words, what we're saying is, give me the union of the set, but subtract away the intersection. So the complement is everything in A and everything in B that isn't in both. Okay, put another way. So we're just going to do away with the intersection. That's called the complement. Let's take a look at how we can achieve that. And you know, I'm going to need to. It would be more convenient if I was working with this result set here. Select color from bands, union, select color from emotions. So what is this whole thing here? This is the union. So if I could take the whole union and then from that pick everything that's not in the intersection, that would be the way of doing it. So here's the union of everything all together. Okay, great. And so let's borrow from what we've learned previously, and rather than having this big unwieldy definition, let's treat it like a temporary table by making it a common table expression. So call it color list as this thing. So now that I've got a sort of a temporary table or a view, if you wish, or what it really is, the common table expression, a CTE. So with that all defined, let's select everything from color list where, here's where we get our exceptions, our filters. So where if the color not in, select color from bands, where color in something, what's that something? Select color from emotion. So do you see what we're doing here? We're basically grabbing everything in our common table expression and then subtracting out what amounts to the intersection. And then we're going to take and order that by color. Let's see, have I got my parentheses balanced? So there's the balanced common table expression, and then I open paren, open a second, close a paren, close a second. Okay, but I'm saying I'm unbalanced here in something where not in. Oh, where color not in. Got to tell it what we're looking for. Color not in. Now we're happy. And let's see what the result is here. And let's see, did we get the complement? Sanity check this. So I should be seeing everything in the purple and everything in the yellow and nothing in the middle of the intersecting region, which is green. So I see blonde, cream, crimson, blonde, cream, crimson, rose, and steel. And I should be seeing brown, gray, orange, and yellow, brown, gray, orange, and yellow. But I shouldn't be seeing black, blue, green. So I'm not seeing black, I'm not seeing blue, I'm not seeing green, nor should I see pink, purple, red, or white. I'm not seeing pink, purple, red, or white. So there we go. So now we've got the complement, and that settles that. So there's a way to emulate each of our set operators in SQL, mini SQL Server, or other SQL engines, Oracle, Postgres, implement some or all of the set operators, or you can easily come up with the equivalent logic in order to give you essentially the same functionality as if it implemented set operators directly. All right, good luck on your assignment.